Okay, so I'm going to talk about how is the modern OpenGL. Usually many people learn the old OpenGL because actually this modern OpenGL is quite new. So in many cases you just learn the old one and then you just learn it's not good enough. So for the photo projection project, I need to learn this. So that's why I will present about this. So these are a little bit the contents of today. So this is one of the first examples when you start learning OpenGL. So usually when you see, this is the kind of thing that you find in internet. But if you actually see this, there is a chance that actually you have no idea what you are doing. Why? Because all of this code has been just deprecated. It means that you can still use it, but soon enough, this will be unsupported. So it means all your code you have will be useless. So in this case, what you have to do? So in this case, just imagine that OpenGL is a phone. It means that you have been using this one, OpenGL, the first version from 1994. However, the last release corresponds to 2010, so you don't like to use the old phone, right? So what will be the difference between one way to work or the other one? So imagine actually the OpenGL is kind of a submarine.
So by the way, I'm just wondering who's responsible for OpenGL these days? SGI is gone, right? So
the ARB, something automatic review board, something like this. Yes, so it's a group which is integrated by IBM, Intel, many big companies. So I think they keep changing.
Okay.
For example, SGI is gone.
So big companies are still involved in this process.
Yes. So, for example, the last, like the major review was in 2010, okay. But the OpenGL 4 point something actually came out maybe 1 year ago, something like this. So it's, yeah. So also NVIDIA is also related to this. So the main difference between both approaches is you, in the graphics pipeline, you start from some vertices or data. So the goal is somehow convert it into pixels, right? So if you think as some kind of flow, what you can do with OpenGL 1 is OpenGL 1 let you access inside, and then it gives you some controls that you can tweak. So you actually don't have any control on how things happen. The pipeline is fixed, but you can somehow tweak some values to get your value. So what actually happens from OpenGL 2 is that actually everything is just chopped, and you are just given a tool set to actually create whatever you want. So since this doesn't make many sense, I'll start with how OpenGL works from the beginning. So this is the graphic pipeline, more or less. So I guess everybody took the class. So this is pretty much it. The only thing in OpenGL 1 that you can actually access is basically this part. You can send some primitives, vertex, colors, texture coordinates, and then more or less everything else, it's done by OpenGL in a fixed way. So you can set some values here. For example, you can decide if it's flat shaded or smooth shaded, but actually just two options. You cannot really control how. So from this point until 2004, that was OpenGL, and this is the old OpenGL. From 2004, the new standard version came out, which is the OpenGL 2.0. This one added some programmable ability in these two parts. So you could actually modify how the transform of the vertex happen, and also how the lighting operations happen. And also in the last part, after the rasterization, on how each coloring could be affected. So from this point, you could start doing some pixel-based shading or lighting, but still it wasn't. It was just some augmented. They give you some functions. You could program very small parts. So from 3.0, the deprecation model is introduced. They decided that from this point, the previous way should not be compatible anymore. So they will keep it compatible, backward compatible for 2 or 3 releases, but they already flag it as don't use it anymore. So what happened here, the main changes is they favorize the shader approach. So it means that everything happens on the GPU. So you send all the data to the GPU. Is actually the GPU who will create its own program and then process everything. So from this point on, it's just the difference is they adding some more control steps. So for example, in this case, they want to add some extra shading step, which is, for example, the geometry shader. The geometry shader can be used to actually modify the vertex positions in real time, or for example, like tessellating, or for example, displacement mapping, these kind of things, which has to be very fast, and it was needed at the time. But for example, since the tessellation was very useful, so they provided some extra refinement step. So they just separated the geometry shader, and they create an extra 2 steps, which they directly tackle the tessellation problem. So why they separate? Because this way they could optimize much more. So now this tessellation step is fully based on hardware, so it's much faster. And from this, nowadays, because of the handheld devices, there is also 2 other standards, which are the OpenGL ES, which is actually based on OpenGL 3, and the WebGL, which is just a JavaScript version of the OpenGL. So in order to make a conclusion, this is how, when you develop a program in OpenGL, shader-based, you should follow these steps. So first you create your shader programs, and then somehow send them to the GPU. Then you fill some data buffers, including the vertex, normals, texture coordinates, then send everything to the GPU, and then the render happens. So in this case, the C++, the OpenGL part is reduced considerably. You just need to create the context, fill the geometry, and then everything else happens on the GPU. So in this case, the shader programmer needs to focus in these 3 areas. So in order to actually program the shader, OpenGL provided their own shading language, which stands for OpenGL shading language, GLSL for short. So it's they try to mimic the C++, but there is some limitations because of the memory constraints. So for example, they only have these data types. There is nothing more. And creating your own data types is limited. You cannot create any type of structure. So for example, they provide, basically since these 4 graphics, they provide data types that are related to graphics operations. For example, matrix vectors, or for example, samplers. Sampler is actually in order to retrieve texture values. So more or less, this means an array of color values. So in order to construct, it's just similar to C++. You can create using constructors. The operators are also simple, but they have been adapted to the use of for graphics. So for example, they provide some matrix operations, some small mathematical library for operating on matrix and vectors. So in this case, these will produce the correct vector in any case. In order to access the components, since it's based on C++, you can access in array mode, but actually you can actually access the different components. So in this case, all of these components means the same. You are accessing the same value. Why? Because depending on which point of the graphic pipeline you are working, there is some how to say, conventions in the naming. For example, if you are working on 3D space, you have X, Y, Z components. If you work on the color space, you will have RGB. And if you work on the texture space, you will have STQ. So in this case, instead of providing these data types, they just put everything together. And also they provide some extra functionalities for accessing. For example, if you want just to get like the first two components, you can type just XY. Then this will mean that actually the first two components of B will be copied to A. So this XY, any combination can be done. So this is very convenient in many cases. And finally, they provide some array functionality. You can create arrays, but there is a very hard constraint. They cannot be dynamic. So the size needs to be specified at compiling time. So this means that when you compile the program, you need to prepare in advance. For example, like if you cannot create infinite number of textures, you need to define somehow. So you need to set some, for example, you could, if you have a large number, but you don't know exactly, you could create a maximum number of textures and then just send what is this top point. Yeah. So there is also a flow control expressions. For example, there is no switch. These are the only ones. And they provide also some built-in functions. So basically how the same are as C++, the mathematical library. There is also some trigonometric. And they also provide some extra functionalities related to graphics. For example, like reflecting a vertex with respect to some plane, or finding the distance, Euclidean distance between points. And well, there is a long list. And you can also define your own functions in the program. However, you cannot just load any external libraries. So that's why they provide many functions by themselves. So here is the most important part. Since the computation happens in two different places, one is in the GPU and the other one is in the CPU, they have to be somehow a communication. So there is two types of communications. One is from the application, the C++ code, to the shader, and also communication between two steps in the shading process. For example, between the vertex shading and the geometry shading, you have somehow to pass the data. So this is done by some special variables. So there are three types of variables. The first one is uniform. The uniform variables are variables that actually the value remain constant for the whole pipeline. So it means that since the moment you send the vertex until this vertex gets shaded as a pixel, this value cannot change. So what kind of data is this? So this could be a light position. It could change in the next iteration, but when the scene is rendered, at this time is fixed. For one frame, this is fixed. Why is this fixed in this time? For example, the projection matrix. The camera will move in the next frame, but not between two vertex. Or the textures, or some other data. This data can only be read. You cannot modify. And you can access this data from either any of the shading steps. But for example, you want to specify some data that needs to be changed for each vertex. For example, normals, or actually the vertex position. So you need another type of data. And this one is specified by the attribute in the OpenGL 3, or they just changed the name, in OpenGL 4. So this one can only be accessed in the vertex shader. So until here, we have talked about the communication between the application and the shader. In order to transfer this data to the next step, you need to specify some out variable. This out variable, the main use is actually you compute, for example, like the user doesn't give the normals from the application. So you can compute the normals, the vertex normals in the vertex shader, and then this data will be transferred to the next step. But this data cannot be transferred just like this. It has to be somehow interpolated. So these variables will do that for you. So you compute one value for each vertex, and then between two vertex, this data will be interpolated automatically. And this can be done by this. So here, and that's why they call it varying in the first step. So basically, in this case, in the vertex shader, it can only be read, write. And then in the next steps, you will actually write or read. And then until the last step, which is the fragment shader, which they can only be read. In order to make more comfortable, so you don't have to define, for example, like the vertex positions or the normals, the GLSL already provides some built-in variables, so you don't need to declare them. You can just use them directly. So these variables correspond, for example, for vertex, the final color, the matrix projections, and anything. So in order to attach your program, you have to compile it. So this is actually how it compiles. So the shaders needs to be compiled on, you can compile it before, but usually they can be compiled on runtime. So if you don't want, this is just compiled directly on memory. They don't produce any file or binary code. So this would be the step. You create the programs, just the object file, the class file. Then you input the source code. Then you compile it. Then you attach it. So attach and link, basically, it means the attach, you can compile many shaders. For example, you can have one shader for computing the depth, one shader computing the color. So you attach them all at the same time. It just means sending them to the GPU. The linking step is actually saying which of these steps will be used. So this time. And finally, the use program is which is the shader that will be used exactly right now. So the only requirements are actually the vertex shader and the fragment shader. Anything in between or multiple passes are not required. So once this is compiled, we defined some variables in the GPU side, in the shader side. So we need somehow to send the data to the GPU. So for example, we have some vertex attribute, for example, like the positions. We somehow need to send them from the application. So how is it done? The process is based on indexing. So basically, you first ask the GPU the index of some variable. You can do this by find the attribute location or find the uniform location at this program, matching this name. So you need to know what are you looking in advance. And then after you bind the data, you set at this index, I'm sending this amount of data. So for example, a simple example here, we find, for example, a vector, for example, the position of the light. So the uniform, because there are several types of uniform, you need to specify which one. So for example here, 4 floats, which is a vector of 4. Then you say the index, which for example here would be like name. And then you specify the 3 values that you specified before. For example, if you wanted to create a matrix, here actually we're sending 3 metrics, 4x4 metrics at the same time. So now I'm going to just show some simple examples. So this is the most simple thing. It just do nothing. The vertex shader, well, it just gets the here is the vertex as sent from the defined in the application, just the coordinates in the object space. And then here we have the model view projection matrix, which change from object space coordinates to the eye coordinates, the camera coordinates. Then it means we just pass it to the next step. Here, for example, in this case, each vertex has a color, so we just transfer this color to the next step. And the coordinates same, the texture coordinates, even though they are not used, we still transfer. And finally, the fragment shader, we just put the same color that has been interpolated. So as you can see, the GL from color is defined as an out variable for the color. So anytime any pixel is required, it will interpolate between the neighboring colors. So an example of why the geometry shader could be useful. For example, like we want to do some exploding geometry. So the very simple principle is we just displace the face along its normal according to some value. So for example, like if this is some weighting value, we can compute the face normal by, here you can see this is the positions. So these are triangles. So the vertex 0, we just compute the cross product between two edges, and then this is the face normal. And then here we just modify the input vertex. We just modify it by the some weight and the normal, and this produces this kind of result. And for example, computing a per pixel lighting, here we need to modify both the vertex shader and the fragment shader. First, we need to compute the normal for each vertex if they are not already given from the application. And then in the fragment shader, we'll compute the viewing vector for each pixel, then getting the light vector, and compute the diffuse and specular contributions according to the Blin equation. So if you remember, the Blin is based on, if this is the normal of the surface, here is the lighting direction, and the eye is here. We have so the trick is to compute the H vector, which the half vector can be computed simply as this kind of thing. And then the diffuse component will be the dot product of just like this. So here if you see in the code, this can be, in this case I just fixed the direction, very simple, just directional lighting. So you compute the half vector. Since the camera is always, we are in eye space, the viewing vector is always the z-axis. So you can see here the z-axis. We sum them and normalize. The normalize is like dividing by the length. Then actually here, yeah, take the color. Here the color, the texture is just blue. And you have the normal. We can normalize to make sure it's 1. And then we compute the dot product between the normal and half vector. And then the specular, yeah. All right. So this is the final equation. So this produced this kind of result. So now just after we can test this in real time, but here are some examples. There are some. Actually, this is the only tutorial I found in OpenGL 4. Even the books, they are still talking about 3, but well, the difference is not that big. So I guess starting. These are good starting points. So before the question, so there is some nice tools that allow to see in real time. So for example, in this case, we have a bunny. And then, as you can see, the shaders here are the simple. So we can, for example, we can simply change the color, all just flat shading. Then compile and link. And now, for every situation, just this color happen. So there is some, you can actually add some time. So for example, so there is some built-in function which is takes the time in seconds from which the application was launched. So now you can see that so you can create very nice things. So if you want to add some texture, you first would define, in this case for a 2D texture is a sampler 2D, then we just call it text. Then you would, for example, the color the texture. I forgot the GL text. Okay, so you compile and link. Then here we just need to define some texture. All right. So, for example, we could just now the texture is messed up, but we can just so here is just some texture with this. So actually, it's good also for developing applications. You don't need to compile. You just rerun the application, and the text, the shaders could be just text files actually, and then they are compiled on runtime. So the development of shaders is much easier than just changing the code, recompiling, and everything.
So if we compare some runtime, the house of performance should be slow with comparison runtime.
But you can see the shader programs are usually not very big. So there is some crazy people. They do everything on the shade and the pixel shader. They just define their own data and ray tracing everything from the pixel. So, okay. Well, this has no. So if you go to Firefox Shader Toy, here actually you can see the. If you click here, there is some real-time demonstration with the code. So these ones takes a little bit more to compile, I guess. But here everything is on the pixel shader, and just the one step you can do shading, ray tracing, almost anything. So it's much more flexible than normal OpenGL. So yeah, if you have some question, then you can ask. or just can look at the tutorials.
So how hard is it or easy is it to learn version 4?
Mm.
How long did it take for you to master?
Uh,
Are you still learning?
I'm still learning. Now I didn't talk about multipath, but you can separate shadings in different steps. So technique called differ lighting. So you compute many things, every light is in one pass. Then you sum everything at the end, which is supposed to be faster. Then there is also ray tracing and these kind of things that can be done in real time. And shading and shadows, so these parts I don't know yet. But I think itself is not that difficult. The problem is using inside Maya. So that I spend many time in this part. But besides this, yeah, just the problem is there is not many information on the web. Like for example, for normal OpenGL, the 1.0, there is many easy tutorials, step by step. In this case, the last resource. This one actually provides many source codes, but very little explanation. So in the beginning it's easy to follow, but in the more advanced tutorials it's difficult. It's more like trial and error and see what happens and compile. And yeah. Okay, thank you.